All right, so normally, a lot of times you'll do these in tabular form. You'll see the book do it in tabular form where it just like identifies areas, 1, 2, 3, 4. And then it just starts to find everything about 1, 2, 3, and 4, like the area, the X bar, the Y bar for that shape, right? So sometimes you'll see it that way and other times you won't. Like if there's a lot of shape, tabular form's kind of a nice way to go, but I always do label them, and you should too, because that's going to help me know what the heck you're doing. And there's more than one way to do some of these. So, you know, you could break it up into different shapes than I break it up into. Oh, there they are. All right, so we need area of 1. And that's going to be the big rectangular solid. That's going to be what? 100 times 100? 10,000? Is that right? 1, 2, 3, 4 millimeters squared? Yeah? No. Oh, you're right. So I don't need to go into X bar and Y bar. So all you need to do is go Ix equals base height cubed over 12. Does that make sense? Yeah. All right. Yeah, no, I was going all the way back to the beginning because I'm all primed up for the transfer one, which you have to first find the silly centroid. So sorry about that. Yeah. So the base is 100. Yep, from here to here. And I'm doing this shape 1. So I'll put a little 1 next to the X. And then the height is also 100 over 12. So Ix of 1, what'd you get? Holy smokes. So let's go 8 point, and then what are the next numbers? 333 e to the 6. Does that look like it works? 8 million? So when you write e to the 6, that just means 6 places, right? To the power of 6. It's like writing 10 to the 6. Same kind of thing, just even shorter, just e to the 6. So that's 8,333,000, blah, 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 blah. Okay. And then the units are to the 4. Yeah, so you got millimeters to the 3rd here, multiplied by millimeters, millimeters to the 4th. Inertia is always to the 4th. All right, so now I'm going to do Ix of the 2nd shape. So this shape, base is 40, height is 70, and that is cubed over 12 rectangles, 2 rectangles. Even though this is a square, treat it as a rectangle, works good. So the 2nd inertia, or the whole, so I'm actually going to note that now as a negative. What'd you get? 1,433 E6. That look right? 1.14333. Okay. Good. And this is negative because it's a hole. And since the large rectangle inertia is located at the centroidal axis, because it's the center of the big rectangle, and then we have a symmetrically placed in the center hole, that axis is also here. And it's very hard to show axes stacked, but that's what we have. One axis on top of the other. When those are on top of each other, you can add and subtract them. No problem. If they are not on top of each other, you cannot add and subtract them. We have to use the transfer formula, which we're going to get to today. So this one's just 8.33 minus 1.143. So that is going to be what we note as Ix. So inertia X is the composite. Inertia X1 is the inertia for shape 1. Inertia X2 would be shape 2 and on more. You know, if there was more shapes, you just keep going. And then when you add them all up, it ends up to be the inertia about this X axis. Sometimes you'll see it written like this, XX, because there's two X's on this axis. I don't write it that way, but. All right, what'd you get? One, excuse me, be 7 point something. E to the 6 millimeters to the 4th. Yeah. Millimeters are kind of weird to get used to. Like, is that a big number? Is that a little number? I don't know. It seems really big, right? But you always end up with a very large number with the metric system in millimeters. So
this is how we be writing them with the decimal.
yeah, we don't need that kind of crazy digits all the way out. This is enough. I carry 3's probably not great. 4 would have been better to have there. But yeah, that's the way I would write it, because when we go to use it, that's accurate enough for this inertia thing. There'll be several areas where we do that. And the reason we're doing that is because everything has a factor of safety on it. So our accuracy is important, but we're also going to be factors of safety below any limits. So if we have a limit of 10, we're not going to ever get to like 10 or 9.96, right? We're going to be like factors of safety below a limit of 10. We're going to be down around 7, 6, or 5. Okay, so the rationale for carrying something out of 7 places just not there.
What's kind of the industry standard?
Like whether you put them down or not.
Well, like, is it just based on the size of the material you're doing, or is it like,
It's based on we're going to read graphs and charts for almost everything. Like when we calculate an inertia, we might look up a beam size that's appropriate based on an inertia. So then you're going to have to like correlate to however that chart comes to you. Does that make sense?
Yeah.
Okay. So like in the back of the book are our charts that we're going to work with, right? So when we start thinking about stress, which is PSI, we might think about it as KSI, which is thousands of PSIs, right? So we can get either one just by that factor of 1,000, but the one we want is the one in the back of the book that we can compare to. So if we're coming up with PSI and I see that I have KSI, 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 then I need to get my number into KSI so I can read this and say, oh, this is good or not good. That makes sense? And that's with like all the charts. So for example, these are steel beam sections in inches to the 4th. So that means I want my inertia in inches to the 4th. There's almost always an SI version of it here. And you'll see that they use 10 to the 3rd millimeters to the 4th. Actually, this is to the 3rd. There's to the 4th. Section modulus is to the 3rd. But we're doing inertia, right? So notice this one's 10 to the 6th. So they're giving us 4 places. So the numbers you just calculated, all you need is 4 places to read this chart. Does that make sense? Does that answer your question? Yeah, it's all about the chart you're going to go to. So when you go to work, like it could be a different chart. If it comes out of like the American National Standard Steel Institute manual, all kinds of crazy units inside there. So you just have to look it up and say, oh, I need that unit because I got to read this chart and I got to see if things work. Inches to the 4th, millimeters. But just watch for those 10 to the 6th or 10 to the 3rd stuff because that'll mess you up. Yeah. Yeah, you're not going to use it. The only thing we're going to use is this. So that's what you're asking. Nope. If they're not in line, we need the individual one. Yeah, because it plugs into the transfer formula is this. That's the individual inertia. So we got to have that number to put it into this formula. Does that make sense? You could. Yep. Yep. As long as it's in inches to the 4th or millimeters to the 4th, then yeah. Yep. All right, let's do this one. Since we are practicing. And I did what you did, hopefully, is just look up some properties first, right? So I took the W1871 and went and found the area just because that's my habit. You're right, we're not going to use it. And then I found the inertia about the x-axis. I didn't pull the y because they didn't ask about the y. Okay, so I just pulled the x. And that's super common. Like most of the stuff we're going to load in its strong position, in this position, we're going to load it that way. We're not going to worry about the y unless we have what's called biaxial loading, then that would be this. So almost everything in the structural architectural world is biaxial loaded. This is biaxially loaded. Like the wind could blow, right, and give us some side load, but more common would be what? Gravity's straight down though, that's this critter, right? Weight and gravity, the Earth's shaking. So even though it's not very common, we design for it big time. So things get massive because we designed for, in this region, I believe we designed for a 7 earthquake, not a 9. That's why all the bridges will be gone if we get a 9. Nothing is designed for a 9. And they say this, you know, the Cascadia big one is going to be like 9. Think about that on your drive home. How many little bridges do you cross to get home? I crossed 22 little bridges to get home. Yeah. So at one time I was thinking, okay, I'm going to rent a storage unit over there, put a motorcycle in it, then I'll be able to get home, you know? All right, that's a little over the top, but it was kind of a fun thought, like, oh, that would be fun. And then what would my route be? You know, my son and I tried to pick the route. Damn rivers. Like, if I go Estacada, I got to get across the flipping Clackamas, which is like a ravine at Estacada. So that wasn't happening. So then if I go 205, I hit the Willamette, it's right there. And then I got another river, the Molalla, to get across, which I could do on a motorcycle if I hit it hard. That'd be exciting. Anyway, sorry, that was a tangent that we recorded. Whoops. All right, so we need the inertia of this one, right? So once we have the inertia of both, then we can just add these up. Yeah, makes sense? So I'll call the W shape 1 and the plates 2. Why would we do this? Any ideas? Yeah, these plates, why would we add those? Extra bending strength, like dramatically different, right? So the W shape by itself is 1170, which has pretty good bending resistance. That's a big number, right? So let's see what the X of the second shape is. Base is 1. I'm just going to do one of them and then multiply by 2 because they're the same. And then the height is 15 inches. Doing a lot of rectangles here, but that's pretty much life. Anyone have that number for me? 281.25 inches to the 4th, yeah? So then the total Ix is going to be Ix of the W shape, 1170 inches to the 4th, plus 2 times 281.25 inches to the 4th. What'd you get? 1732 point. So from 1170 to 1732. Drove it up pretty good, didn't double it, right? So when you see this stuff, when I've done this, designing trailers, they really wanted us to use available steel that we had in the yard, and we had a pretty big yard of steel. But I would find something, go do the calculations. It would be just short of what I needed, and I'd just find some plate steel and say, let's just weld this onto the, onto the web, and we'll have enough and go. So you see it like that, and then you also see it in reinforcement in areas of excessive bending stress. So if you watch next time a trailer, big semi-truck trailer goes by you on the freeway, just look at that structural beam that's carrying it all. And a lot of times that structural beam, it might even taper. But if it doesn't taper, you'll see areas of plates just welded on. And those are just high stress areas where they need to drive up the inertia so it can carry that bending resistance in those spaces. So it doesn't have to be full length. It can be just over a region. Like when we do bending stress, we'll calculate bending stress at an exact spot on a beam, and then another spot and another spot. And then we'll be able to build the graph of that and find out where it's very high stressed, where that highest stress point is. And then we could just reinforce that area with some plate, drive the inertia up. Cool. All right. Questions about any of it?